Video we're going to talk about the back propagation, and we will also delve into the choice of which activation function should we prefer. And we'll start with the sigmoid, and we will see the problem in the sigmoid function. And let's start with our simple neural network. We have two inputs, which are the features, and then we have one hidden layer with two neurons, which are both using sigmoid activation. Then in the output layer, we also have sigmoid, and our loss function is here. So first, let's start with the fast forward. What do? We calculate the linear combination, the weighted sum of here, which is sigma z1, and then we calculate the weighted sum for this activation, which is sigma z2, and then we have other, of course, we also have the parameter b1 and b2, and then sigma z1, sigma z2. We calculate the weighted sum here again, and then at the end we calculate the sigmoid activation function. Then it will give us a value between 0 and 1. So in here in the output layer, using a sigmoid is okay, because using a sigmoid function in the hidden layer purely depends on our problem. If our problem is a binary classification, then it's okay to use sigmoid in the hidden layer, in the output layer. But sigmoid functions are not almost used never in the hidden layers, and I will tell you why. So in our backpropagation problem, before delving into why sigmoid is not a good idea to use in the hidden layers, we're going to talk about the backpropagation. So backpropagation is basically, and let me tell you that we are using batch gradient, so actually, but what I've written here is still true. But in the batch gradient, we just run all of the training samples. I'm only showing you one training sample here with two features. We run all of the training samples, then we calculate the loss for each one. Then at the end, we just take the average loss of all the samples. And after doing that, we go back and then we calculate the gradient with respect to all of the parameters with backpropagation. So we have this function here, then we calculate the derivative of this function, and we're going to use the chain rule. We use the derivative of this, we calculate the derivative of this loss function with respect to y hat, our prediction, as you can see here. Then we multiply it by the derivative of our prediction with respect to this activation, and then we multiply it by the because this here depends on Z3, right? Because we had Z3 a combination, linear combination, then we fed it to sigma Z3. And then we go the same way, the derivative of sigmoid Z3 with respect to the weighted sum of Z3, and we multiply it by the derivative of weighted sum Z3, and we calculate the derivative of this with respect to Z1, because Z1 contains W1. Z1, then at the end, the derivative of Z1 with respect to V1. and then the answer we get is basically this the derivative of our loss function with respect to our w1 parameter. And as you can see, the problem actually happens here. So one of the problems of sigmoid is that the maximum derivative that it can give us is 0.25, which is not a big number. And because of this, the gradients can get very small. For example, if we had another layer here, which also used the sigmoid function, then we will also we would multiply this with the derivative of this, derivative of sigmoid z2 with respect to the z2, then this number would actually become even smaller. So that's why when the gradient gets very small, it becomes very difficult for our neural network to update the parameters, and it becomes very slow, because each time we only update our parameters tiny bit in order to get to the optimum. So that's why in this case sigmoid is not a good idea to use in the hidden layers. And another problem with the sigmoid is that if is that the sign is propagated through this chain rule. So if at one point the derivative of the sigmoid gives us a positive sign, then it means that it will also follow a positive. So the gradient at one point forces the gradients of the other layers to be positive or negative. So this is not something that we want. We don't want anything to force our parameters to go in one specific direction, and that's why sigmoid is not a good activation function, because sigmoid, for example, gives us a value between 0 and 1, and here in the hidden layer the sign will be propagated, so we don't want to have this. So then what is the solution? We have another activation called 10H, which is, it's actually 10Z, and 10Z is basically 2 sigmoid 2Z minus 1, and its value is centered around 0, because it can give us value between -1 and 1. And this is great, and the thing is, the maximum derivative that it can give us is 1, so way better than sigmoid. So it will mitigate the problem of vanishing gradient, and also it will not force any direction in our gradient chain, which is great. But still, for some, it's the maximum is 1, and between 0 and 1 the derivative. And the thing here is that we still have vanishing gradient problem, even though we have mitigated it. Then we can solve this with a ReLU activation function, which is basically max 0 z. So given a value, if it's bigger than 0, then we just basically output z, and if it's smaller than, if it's a negative value, then we just give 0. And here, the problem of vanishing gradient is solved almost, because when we take a gradient of a loss function with respect to ReLU activation function, we will not get values that are very close to 0, and it solves this problem. But another problem that ReLU introduces is how he handles, negative outputs, because when ReLU gives us 0, and when we take the derivative of our when we take a derivative of the loss function or with respect to ReLU, we get 0, and then the gradient becomes 0, and when the gradient becomes 0, the parameters that goes through this neuron that uses ReLU will never be updated. So we will call this neuron a dead neuron. So that is one of the problems. If we have a huge neural network and we only have few dead neurons, that wouldn't be a problem. But if it's more, then it becomes a problem. Then we can introduce a leaky ReLU, which still allows a small value for negative um, negative outputs. So when z is negative, we will not output 0, but instead we will output something like a small value.